discussing? We'll be discussing about one common proof that Maxwell brought all the relations, for example the Gauss law, Faraday's law, Ampere's law, into one common proof known as the Maxwell's law. These are relations which are in integral form. So when we say that these are relations in integral form, that all the relations are given in the form of integration, because there is also a differential analog possible for this. Right? Now coming back, Maxwell's first relation basically is nothing but the Gauss law. So if you have a single charge which is present in a particular vicinity, as a result there is going to be some electric field produced. In the same way, we talk about the case of magnetic field, that relation is equal to 0 on the right hand side. Reason being, there are no magnetic monopoles. Then there are Ampere's law and the Faraday's law, which basically relate the circuitous motion of the electric field and magnetic field. So what did Maxwell do into it? The Maxwell added a term which is known as a displacement current. Displacement current is proves to be very essential to understand about the fluctuating values of electric field and magnetic field. So stay tuned into this particular chapter, listen to it very carefully, you'll get to know the origin of the displacement current. So now we begin on with the next part, that is the Maxwell's equations. So let's try to understand about the Maxwell's equations. We are aware about the few different equations which we are aware, like the Faraday's law, the Ampere's law, the Gauss theorem and so on, right? So Maxwell basically combined all of that and wrote down the equation like Maxwell's equations. So from the Maxwell equations, it was very easy to identify what should be the equations which are going to satisfy all of these, yeah, the wave equations which are going to satisfy exactly all the equations which were defined by Maxwell's. So let's go further and try to identify. So here, when we talk about the electricity and magnetism, all of that can be combined together to form the electromagnetic waves. So here, when we talk about this, first equation that we know is the Gauss law. So Gauss law tells us that it's basically if any particular region has a charge enclosed in it, then the electric field in that particular vicinity can be found from this particular relation, that is integration of E dot ds is equals to q by epsilon naught. So this is the Gauss law for electricity. But we are completely aware that we can have a standalone positive charge and a standalone negative charge, right? So these charges can exist on their own. As a result, the Gauss law exists for both positive charge and negative charge. It's just that the direction of flux changes. But for the case of magnetism, there is nothing like a standalone positive charge or standalone negative charge. There are no standard charges. Yeah. So there are no magnetic monopoles to be precise. So if there are no magnetic monopoles which exist, so for the case of magnetism, the total magnetic field over a given area, that is, this is the case. So since there are no magnetic monopoles which exist, so total magnetic field over a given area, if you just try to find out over the total area, that is going to be equals to 0, because there is no single charge, no single magnetic monopole existing. Going further, if you talk about the Ampere's law, Ampere's law is basically B dot dl, that is equals to mu naught into I, which we are aware of it. Yeah. In addition to that, what we do, we add a factor of d phi by dt. So when epsilon naught d phi by dt, so when we add that part, so that gives rise to the extra bit, which is the displacement current. So here comes the displacement current. Yes. In an analogous way, the variation, so it should actually be equals to, this should actually be given by E dot dl. So if I talk about E dot dl, so this is going to be equals to mu naught I, plus there is going to be the variation, the flux variation in terms of the electric flux. So one is going to be in terms of the magnetic flux, other one is going to be in terms of the electric flux. So combining all of this together gives rise to what are known as the Maxwell's equations. Let's go further from here. So what exactly are the Maxwell's equations? So we have already written them down. We know that when we are in vacuum, there are no single charges and therefore there are no conduction currents. So the Faraday's law and the Ampere's law take the form like normal E dot dl, which is equals to minus d phi b by dt. So this is the equation, and for the case of Ampere's law, so B dot dl, which is equals to the displacement current that we are aware of. So as a result, if you just try to put in the equations, so for the case of electric field, so let me just try putting in here. So let's say this is our y-axis, this is our x-axis, sorry, z-axis, and let's say this is our x-axis, right? Now let's try to identify and talk about the different waves that are there. So if you talk about for the case of electric field, the electric field waves vary like this. If you talk about for the case of magnetic field, so for the case of magnetic field, the magnetic field waves are going to vary like this. So as you see, the oscillations are taking place along perpendicular directions like here and here. So electric field is oscillating along the y-axis, magnetic field is oscillating about the z-axis, but both of them are propagating along the x-axis. So that is the most important thing to be understood. And both these equations actually come from these two equations, which are as a result of the Maxwell's relation itself. So the wave described above propagates along the positive x direction, the electric field remains along the y direction, and the magnetic field along the z direction. The magnitudes of the field oscillate between this and this. So again, let me come here. So you see that, let me change the color. So here the maximum magnetic field value is going to be equals to B0. Similarly, this value is going to be equals to minus B0. If you talk about for the case of, if I talk about for the case of electric field, so this is going to be E0, and similarly this is going to be equals to minus E0. So this is how the electric field and magnetic fields actually oscillate with time, right?